What if you could build a computer so ridiculously powerful it could solve problems that our best supercomputers today wouldn't finish in a million years? Well, that's the whole promise of quantum computing. And believe me, this isn't science fiction anymore. It's a full-on global race to build the future. So what lit the fuse on this revolution? Let's get into it.
Here's how we're going to break it all down. We'll start with the impossible problem that got us here, then look at the radical idea that changed everything. After that, we'll cover the breakthroughs that made it real, dig into why the race is so intense right now, and finally, ask, what's the next quantum leap going to look like for all of us? You know, this whole story really starts with a wall. A point where, for all their incredible power, the computers that run our entire world just stop. They hit a problem they simply cannot solve. Let's look at why. Which brings us to the fundamental question that kicked this whole thing off. Why? Why are there certain problems that are just plain impossible for even the fastest supercomputers we can possibly build? The answer comes down to this thing called exponential complexity. Okay, think of it like this. Imagine you're trying to find the right key for a lock. If you have 10 keys, no problem. But what if for every key you add, the number of possible combinations doubles? The problem explodes so fast it becomes totally uncontrollable. That's exactly what happens when we try to simulate a complex molecule or crack modern encryption. A classical computer just gets buried, facing a task that would literally take millions of years. It's a fundamental roadblock. So, with our best computers stuck at a dead end, the world needed a completely different kind of answer. And it came from the legendary physicist Richard Feynman, who had this brilliant, almost simple idea. If you want to simulate nature, your computer has to act like nature. And back in 1981, Richard Feynman, in his classic, blunt way, pretty much said it all. He realized that down at the subatomic level, nature doesn't play by the simple on or off rules of our computers. It's weird. It's quantum mechanical. And his insight was just profound. To solve quantum problems, you need a quantum computer. And this is the absolute core of quantum computing. A normal computer bit, right, it's like a light switch. It's either on, a 1, or it's off, a 0. Simple. But a quantum bit, or a qubit, is more like a dimmer switch. It can be on, off, or anywhere in between. And here's the crazy part, all at the same time. It's a principle called superposition. By harnessing this weirdness, a quantum computer can explore a mind-boggling number of possibilities all at once. It's a power Feynman knew would be revolutionary. So how did Feynman's wild idea from the 80s turn into this massive race to build actual machines today? Well, it didn't happen overnight. It happened through a series of absolute game-changing breakthroughs. Okay, so in the 80s, you had Feynman and others proposing the basic models, but the real game changer was Shor's algorithm in 1994. We'll get to that in a sec. Then came Grover's algorithm for search, then the first time a quantum algorithm was actually run in 2001, and finally, Google's 2019 claim of quantum supremacy. Now, that claim was pretty controversial, but it was still a huge moment. Each one of these steps turned what seemed impossible into something, well, inevitable. Now, to really feel the power we're talking about, just look at this comparison. Peter Shor's algorithm proved that a powerful enough quantum computer could crack the kind of encryption that protects our banks, our governments, everything, in just a matter of hours. A task that would take a classical supercomputer thousands of years. Suddenly, the entire digital world we built looked fragile. All right, so the theory is powerful. We get it. But why is there this massive billion-dollar race to build these things right now? It really boils down to two things. We're hitting a wall, and we're seeing an incredible demand. See, for decades, progress was pretty predictable. It was defined by Moore's law. Basically, the number of transistors on a chip doubling every 2 years, making them faster and more powerful. But that party is ending. We are hitting the absolute physical limits of how small we can make these things. So to keep moving forward, we don't just need a better chip, we need a whole new kind of computer. And the stakes for getting this right, they couldn't be higher. We are talking about designing new life-saving drugs by perfectly simulating molecules, creating truly unbreakable codes, optimizing the entire global financial market, and unlocking the next generation of artificial intelligence. These are multi-trillion-dollar opportunities, for sure. And hey, just so you know, this isn't some far-off dream. This is already happening. Take Moderna, a company we're all very familiar with now. They're working with IBM to figure out how quantum computing can help speed up future vaccine development.
The potential for real-world impact is what's really driving this race forward today. So, we've got the problem, we've got the big idea, and we've got this global race that's heating up every single day. But, and this is a really big but, the path forward is anything but easy. Let's talk about the massive hurdles and the huge questions that are going to define the next quantum leap. You see, building these machines is just ridiculously hard. The qubits, the heart of the machine, are unbelievably fragile. The slightest vibration, a tiny change in temperature, what scientists just call noise, can completely wreck a calculation. Keeping them in that special quantum state, something called coherence, is a constant battle. And trying to scale up from a handful of these fragile qubits to the thousands or millions needed for the really useful stuff, that is one of the biggest engineering challenges of our time. And that brings us to our final and maybe the most crucial question of all. Given the power to break any code and solve these immense problems, this race isn't just between big tech companies, it's between nations. So what happens when one of them finally gets there? When one nation achieves true functional quantum supremacy first? The answer to that question is absolutely going to shape the 21st century.